Now, this is interesting. We're in chapter 4. I thought we were in chapter 5, right? Well, the thing is that the next section that we're going to talk about, and we'll talk about this section on Tuesday, in Tuesday's class, is section 5.10, improper integrals. But in order to do some improper integrals, we have to have knowledge of finding limits. Improper integrals are actually limits of integrals. And so L'Hopital's rule is helpful in determining some of these limits. So what is this L'Hopital's rule? Well, they have here, and I'll give you a little guided tour here. You have here a function. Well, let's say you wanted to know the value of the limit as of the function, the quotient function, log of x over x minus 1. You want to know that limit as x approaches 1. Okay, how many recall, by the way, in Calculus 1, finding limits of functions? I hope you recall that. Sure, that's what a derivative is, right? Derivative is a limit of a quotient. Good, good. Thank you, everybody. So, but you see, sometimes there are limits that are what are called indeterminate. So, like for instance, this in box 1 here, and again, we're in section 4.5. What does the log of x do as x approaches 1 in the numerator? This in the box there, box 1, we want the limit of the log of x over x minus 1 as x approaches 1. How does the log function behave as x approaches 1? What is the log function? Well, what is the log of 1? What is the log of 1 equal to?
0.
0. Good, that's right. It equals 0. And what is in the denominator 1 minus 1? What does that equals 0 also? So you see, you have a numerator and denominator that are both approaching 0 as x approaches 1. Okay, so you get what's called an indeterminate form. 0 over 0 is, I mean, well, it's never going to equal exactly 0 over 0 because you're taking the limit, right? But the thing is, we just don't know for sure what that limit approaches because 0 divided by 0 is an indeterminate form. Okay, and so we need something to help us. Okay, and it turns out, well, yeah, in general, and they comment right here, I'll highlight it. Okay, if you have a limit as x approaches a, if you have the limit of f of x over g of x as x approaches a, where f and g both approach 0, then this limit may or may not exist, and it's called what's called an indeterminate form. Okay. Now, for some rational functions, you can find what that limit is. So like the limit of x squared minus x divided by x squared minus 1 as x approaches 1, you can factor the numerator and denominator, and then you get some simplification, and that equals a half. That equals a half. Okay. And so you computed, how many recall doing limits like that before in Calculus 1? Ones where you, sure, Marcus remembers that, and Nicole and others. Also, yeah, I don't know if you had done this in your Calculus 1 class, but there's how many have seen this famous limit, the limit of sine of x over x as x approaches 0, that equals 1. Okay, Jacob recalls that, and hold on here. Some others, I didn't get all the names, but that's something that some professors cover, and they use a geometric argument, but it's messy, right? It's messy. So what we're going to do is, and I think somebody has their mic on there. What we're going to do? Oh, okay, okay. Is there? Okay, thank you. So we need a way to handle these indeterminate forms. And we're going to use, well, I'm going to show you something else too. If you, let's focus on this indeterminate form. Okay, suppose you have the limit of a ratio of functions f and g as x approaches a, where both functions either go to infinity or negative infinity. That's another type of indeterminate form. Okay, because what really depends, what really causes the limit to compute the limit. What's important, of course, is the rate at which these functions approach infinity or negative infinity. And so we need a way to determine the limits of these indeterminate forms. And there's a special rule called L'Hopital's rule. L'Hopital's rule says that if you have two differentiable functions, this is section 4.5, if you have two functions that are differentiable, that means you can take derivatives, right? And the derivative of g with respect to x is not equal to 0 near a, okay, then if both of these functions approach 0, or if both of these functions approach infinity in their limits, in other words, if you have an indeterminate form, 0 over 0 or infinity over infinity, then the limit of f over g is equal to the limit of the derivatives, f prime over g prime. That's called L'Hopital's rule. Okay, L'Hopital's rule is used for finding limits of indeterminate forms of the type 0 over 0 or infinity over infinity. Okay, that's called L'Hopital's rule. And again, this is the key rule. This is the key thing right here. The limit of f over g is equal to the limit of f prime over g prime. Now, this is only true if you have indeterminate forms, 0 over 0 or infinity over infinity. And we'll look at a few examples. But you might wonder, well, why is this true? Why is this true? How is this true? Well, they have a figure here that suggests why it might be true. Take a look at the figure. You have here in figure 1, you have a function f and a function g. And what do f and g in figure 1 there at the top picture, what do those functions approach as x approaches a? Okay. What do those two functions approach? Okay, and I'm just waving hi to show you that I'm alive, I'm a human, teaching you all. Good to see you. Good. Okay, so they're both those functions f and g are good. They're approaching 0. Hold on, who chatted that? Man, yes, that's right. Jacob and Sean. They approach 0. But in the second picture, well, so what would happen if in figure 1, the first picture, what if we were to zoom in on the picture near that point A0, that coordinate A0, where x equals a, right where those two functions equal 0 there. If we were to zoom in on that, do you see that both functions would appear to be linear looking? I mean, what I'm trying to say, here's what I'm trying to say. Let me show you here. Hold on. One moment. Okay, so if you have a function, okay, okay, and you have a point on the function, and you look at just a little bit a little bit of the function, okay, over a very small range there, small range of x, doesn't the function look linear? I mean, if you concentrate on looking at the function just at for a very small piece of the function, okay, doesn't the function appear to look linear? Yeah, and yeah, it does. It does. Good, Sophie. Good, good, and Michelle. Good. So we're gonna take advantage of that, because what we can do is we can say, okay, back to the figure here, back to figure 1. What we can do is we can say, okay, well, we could approximate the functions f and g at that point a0 with tangent lines. And the tangent lines, like for instance, like for the function f, the tangent line is y equals m1 times x minus a. Okay, where m1 is the derivative. Now let's see if I can justify that. Let me go back to the whiteboard here. Hold on. Okay, so let's say that at x equals a, let's say that hold on. At x equals a, f prime of a is equal to m1. Okay, we'll call f prime of a the derivative of m1. Okay, so the point slope form of a line is y minus y1 equals x times x minus x1, right? And we note here that at x equals a, of course, we're concentrating in that figure 1 about the point a0. So y minus 0 equals m1 times x minus 0. Sorry, I should say y minus a equals m1 times x minus 0. And therefore, y minus a equals m1 times x. And so y equals, hold on here. One moment, everybody. Yeah. Hold on here. Yeah, y equals, hold on here. I'm not sure I like what I'm seeing here. Hold on, class. Oh, I got an error. Yeah, I do. I had it right the first time. Hold on here. Yeah, I see it. Hold on. Thank you. This is 0. I mean, here's the point, a0. So y1 is 0. And x1 is a. So that means y equals m1 times x minus a. This is an equation of the tangent line for that function f at the point a0. So again, this is the tangent line to the function f at the point a0. Let me just make sure I got everything in here okay. This is an a, right? Right. Yeah, yeah. So now if I go back to the picture, it makes sense. It makes sense, these tangent lines, the equations. Now, so F divided by G is the same as the ratio of those two tangent lines, right? It's the same as the ratio of those two tangent lines. Well, what happens? What happens then? If we hold on here. Yeah, this is what I want right here. So the ratio of the two tangent lines is equal to m1 over m2. Okay, so like well, yeah, and so that's the ratio of the derivatives. So therefore, the limit of f of x over g of x as x approaches a is equal to the limit of the ratio of the derivatives as x approaches a, because it's the derivatives are slopes. So the ratio of two slopes is the same as the ratio of two derivatives. Does that help you feel comfortable with L'Hopital's rule? Was this helpful? Maybe give me a thumbs up if this was helpful to you. Okay, good, good. Thank you. Thank you, everybody. Wow, excellent. Appreciate all the participation there and the positive feedback. Okay, so now with L'Hopital's rule in hand, we are, and again, let me just bring up there's the L'Hopital's rule. There it is. And now we're going to use it to help us find some limits. So on that note, let me go in here to bring up some notes. And let's take a look, first of all, at that famous example. Okay, let me give you a moment to copy it down. Okay, so what does the sine of x approach as x goes to 0? What's the sine of x approach? What value? It approaches 0. That's right, Marcus. What does x approach? What does x approach as x approaches 0? That's hopefully easy. That's right, Sean, 0. So we have an indeterminate form here of 0 over 0. And because we have that indeterminate form, we can use L'Hopital's rule. Okay, so let's go ahead and look at the solution. By L'Hopital's rule, and when we use L'Hopital's rule, we put an H above the equal sign. H stands for, the H in L'Hopital's rule. So you have here, and maybe I'll put this in, add a little thing here. You have f over g, the limit of sine of x over x as x goes to 0. By L'Hopital's rule, that equals the limit as x of f prime over G prime as x goes to 0. Well, the derivative of the sine is the cosine, and the derivative of x is 1. So you get the limit as x goes to 0 of the cosine of x, and the cosine will equal 1 when x goes to 0. So we found the limit. Jacob, was that a lot easier than the geometric argument you learned? I think you were the ones who told me your professor showed you how to do that that limit geometrically, right?
Yeah, it was so much easier. My goodness.
So much easier. Okay. Knowledge is power. Knowledge is power. Okay. And unfortunately, in Calculus 1, they don't cover the L'Hopital's rule because I think they want it covered more closely to when you're, well, I don't know. They just don't, you know. But we're covering it now. So, and it's part of the course to cover this. So, are there any questions? Okay. Well, let's go ahead here and let's look at a few other, at some more problems. Okay. Let me give you a moment to copy this example down. Okay, so we have the limit as x approaches infinity of x times the sine of pi over x. This is kind of interesting. So do we have an f over g here? Do we have the ratio of two functions? Or do we have the product of two functions?
Product.
A product. Okay, well now, L'Hopital's rule says that we have to have a ratio of two functions, and the indeterminate form is either 0 over 0 or like plus or minus infinity over plus or minus infinity. So if now, the thing is, well, can we find this limit? Well, let's see here. What does as x goes to infinity, x goes to infinity. What does pi over x go to as x goes to infinity? What does pi divided by x go to? Goes to 0. So then, that's right, Sean, good. So let's see. We have x going to infinity, and then what the sine of pi over x, the sine of pi over x would go to what? X goes to infinity, and the sine of pi over x goes to what? As it goes to, I got it. Hold on. I'm going to do it like this. Let me do this a little better. Hold on. Yeah. X goes to infinity, and the sine of pi over x goes to the sine of 0. But what is the sine of 0? That's 0. So you have here, one function going to infinity, another function going to 0. This is an indeterminate form. This is indeterminate. We don't know. We don't know. You got one function getting bigger times another function getting smaller. It's like an arm wrestling contest. Who wins? Who wins? It really depends on the rates at which these functions go to infinity and 0. Question, Samuel?
Never mind, I figured it out.
Okay. Well, maybe what we can do is we can't apply L'Hopital's rule to the product of these two functions as is. But we maybe can write the product of the two functions as a quotient of two functions. And that's what we're going to do. That's what we're going to do. So on the next page here, okay, we have the limit as x approaches infinity of x times the sine of pi over x. And what I'm going to do is I'm going to multiply the top and bottom by 1 over x. I'm not changing the limit at all because 1 over x divided by 1 over x is just equal to 1, right? So I'm not changing the limit. I'm just rewriting the limit. Now what happens, of course, is in the numerator, you have an x here and you have an x there. They're gonna simplify out, right? They're gonna simplify out, and you'll get the limit as of sine of pi over x over 1 over x as x approaches infinity. So now let's see. Let's take a look at this. As x goes to infinity, what does 1 over x approach as x goes to infinity? 1 over x is going to go to
0.
to 0. And the sine of pi over x is going to go to the sine of 0, which is 0. So now you have an indeterminate form that you can use L'Hopital on. You can use the L'Hopital rule now to help you find this limit. Okay. Are there any questions up to here? Okay, well, so before I take derivatives, I'm going to, generally quotients like pi over x, I like to write as pi times x to the negative first power. And 1 over x is x to the negative first, because it's easier to use the power rule than the quotient rule to compute a derivative. So now I apply the L'Hopital's rule. Now I apply it. Okay, again, in the numerator here, this is my f function, and in the denominator, this is my g function. So using L'Hopital's rule, I take the derivative of the numerator, that's f prime, and divide it by the derivative of the denominator. And take the limit of that. It turns out that some nice things happen here. These x to the negative second powers simplify out. And you have a negative over a negative. That becomes, and you end up with this. You end up with the limit as x, the limit of pi over x times cosine of pi over x as x approaches infinity. Well, we know that the cosine of pi over x as x approaches infinity is going to approach cosine of 0. Try to make that, and that just equals 1. Make that a little nicer. Get used to my stylus now a little better. I guess. That approaches the cosine of 0. Okay, and as x goes to infinity. So, wow, pi, you get pi. So who would have thought that the limit as of x times the sine of pi over x, who would have thought that limit as x goes to infinity equals pi? But it does. It does. Okay. Are there any questions? Who's feeling good so far with it? Okay, Jacob is. Nicole, good. And Jazi and Audra, wonderful. Okay, well let's move to another example if we're all good. Okay, take a look at this one. I'll give you a moment to copy this example down. Okay, so here we have the difference of two functions. Okay, so we can't use L'Hopital right now, but of course the secant of x is what? How do we define the secant of x? That's, do you remember from your trig days? Well, let's do the tangent's probably easier. The tangent is what over what? Yeah, sine of x over cosine of x. And the secant is?
1 over cosine of x.
That's right, good. Good, Samuel, 1 over cosine of x. So what happens to, as x goes to 90 degrees, to pi over 2, what do both the secant and the tangent go to? It might be easier to look at the how they're defined. Being that the secant has a cosine in the denominator, what's the cosine go to? What's the cosine of 90 degrees? Or what's the cosine of pi over 2? 0. So secant of x is going to go to 0. And tangent of x is going to go to 0. Okay? So you have here another indeterminate form. Now hold on, wait. I'm wrong on that. Tangent, wait. No, the tangent of x will go to infinity, right? There's an asymptote at pi over 2. Remember the tangent function? When you graph the tangent function, try to do this. Hold on, let me just try that. Come on, give me that marker. Man, it's tough. It's just hard to do here. All right, so tangent, here's an x and a y-axis, and tangent function looks like. See, the problem is I got to keep hitting different things to get. So tangent function looks like that, right? Roughly. It's not the best picture, but. And there is an asymptote at pi over 2. How many recall the graph of the tangent function? Yeah, there's an asymptote at pi over 2. And so what happens is you have one function approaching 0. Hold on here. I said this wrong. Hold on. I mean, not every. Yeah, it's infinity, right? So, cosine of x, the secant of x is 1 over cosine of x. Tangent of x is sine of x over cosine of x. So the fact that the cosine of x goes to 0, this goes to 0, and this goes to 0 as x approaches pi over 2, means that you have infinity minus infinity here. That's another indeterminate form. That is another indeterminate form. You don't know which is going to infinity at a quicker rate. Is one beating out the other? It's an indeterminate form. So we have to rewrite that function. Thank you, Leping. Very good. We have to rewrite that function, or rewrite those functions, and look, the secant is 1 over the cosine, the tangent sine over cosine. Why don't I just combine those fractions? Okay, I'll combine those fractions, and now I think we can use L'Hopital's rule, because as x approaches pi over 2 from the left, but it's approaching pi over 2, 1 minus the sine of x is going to approach 1 minus 1, which is 0. And the cosine of x is going to approach 0, right? It's going to approach the cosine. Well, let me rephrase it. I want to rephrase it. 1 minus the sine of x will approach 1 minus the sine of pi over 2. That's 1 minus 1, that's 0. On the other hand, the cosine of x is going to approach the cosine of pi over 2, and that's 0 also. So you have now an indeterminate form of 0 over 0, and you can apply the L'Hopital's rule. And turns out you'll get a 0, because when you apply L'Hopital's rule, yeah, you get negative cosine of x over negative sine of x. As x approaches 90 degrees, cosine's going to go to 0 and sine's going to go to 1. So you get 0 over 1. Okay. Are there any questions on that? Okay, let's do one more here. let's do one more. Let me see here. Just give me a moment here. Hold on. Okay. Wow, look at this one. All right, so here, let's remind ourselves as x goes to 0, 1 plus the sine of 4 over x is going to approach 1 plus 4 times the sine of 4 times 0. That's just going to equal 1. The cotangent of x is going to approach cotangent is the cosine of 0 over the sine of 0, because cotangent is cosine over sine. That's going to equal what? What would the cosine of 0 divided by the sine of 0 equal? That's 1 over 0, right? What's 1 over 0 equal to?
No.
Yeah, I got to be a little careful. Yeah. I was going to say it's the limit. It's going to. What I'm trying to say is this goes to infinity, right? Because you can't divide by 0, but you're taking the limit. So you got something going to 1 in the numerator, and then something going to 0 in the denominator. So you have an indeterminate form of 1 to the infinity power. That's an indeterminate form. That's indeterminate. 1 to the infinity power, that's indeterminate. Because you have something, it's approaching 1, but it could be less than 1, and you're raising it to the infinite power. So if you take a fraction smaller than 1 and raise it to a high power, it's gonna go to well, we don't know what it's gonna go to. It could go to 0, it could go to infinity, it could do anything. Okay, it's what's called indeterminate. So what we have to do is we have to rewrite this rather ugly function. We have to rewrite it. And if we do that, what we're going to do is we're going to let y equal 1 plus the sine of 4x raised to the cotangent of x power, and we're going to take the log of both sides. Okay, now I'll show you why this works, but just trust me for now. We got to do something to simplify this expression. So instead of looking at the limit of that function as is, I'm going to study the limit of the log of that function, because that's easier to work with. So I take the log of, I define y as my function, 1 plus the sine of 4x raised to the cotangent of x power, and then I take the log of it. I take the logarithm of it right here. Well, we know how to apply log rules, right? We know how to apply log rules. The log, the natural log of a to the bth power equals what?
B ln A.
That's right. That's right. And that's what I've done here. But to apply L'Hopital's rule, I need a quotient. So the cotangent, remember, is the same as 1 divided by the tangent of x. And so this tangent can be then, it's there in the denominator. I can rewrite the product of those two functions as a quotient of these two functions here. And both functions, as x goes to 0, both functions go to 0. The log of, the log of 1 plus the sine of 4x, this on top here, let me just, this on top is going to go to the log of 1, and the tangent of x is going to go towards the tangent of 0. And both of those are 0. So we have indeterminate form 0 over 0, and I can use L'Hopital's rule. And that's what I did here. Chain rule on the top, and the derivative of the tangent on the bottom is secant squared. Okay. And now we can put in x equals 0 and evaluate that. And when we do, we get 4. Absolutely amazing. Absolutely amazing. Please let me know if you have any questions. Yes, Samuel. Oh, I can't hear you, Samuel. Hold on. I still can't hear you, Samuel.
I just realized I was muted. Okay.
Okay.
So, okay, ln x is 1 over x, and that's why it's 1 plus sine over 4x. I mean, 1
That's
over 1 plus sine 4x, and then
the derivative of the cosine of the sine of 4x is, by the chain rule, cosine of 4x times 4.
And then the derivative of tangent is just secant squared x?
That's correct. And then all right, very good. And then when we put 0 in everywhere, we'll get, we'll get all this good stuff. But now what I found is I found the limit of the log of y as x approaches 0. And that's nice. That's good. But in other words, but I need, here's what I, hold on here. Here's what I know. Here's what I know. Okay, here's what I know. I know now that the limit as x, the limit as x approaches 0 from the right of the log of y, that equals 4. That equals 4. But I want, let me rephrase it again here. Hold on. So after this, now I know the limit as x approaches 0 from the right of the log of y, that equals 4. But I want the limit as x approaches 0 from the right of y, not the log of y. I found the limit of the log of y as x approaches 0 from the right, but I want the limit of just y as x approaches 0 from the right, because y was defined as my function. So how, I mean, what do you think the limit's going to be? What do you think this has to be, that limit? What does this limit here you think have to be? Given this fact here, we're going from log of y to y. Good, Sean. Somebody else, was that Nathan or Samuel, who said e to the fourth is right? That's what the limit's going to be. So let me show you here formally. This is, you know, what we're looking to find. We're looking to find that limit. That limit is just the limit of y as x goes to 0 from the right. But y can be written as e to the log of y. And I know the limit of the log of y as x approaches 0 from the right. And so I get e to the fourth power. Isn't that amazing? How many think that's pretty amazing? Yeah, Jacob's liking it. Michelle likes it.
Could you really quickly say why it can be written as e log of y? For some reason, I'm blanking.
Well, exponential and log functions are the it's sort of like if you had the square root of x squared. That equals x. Actually, it's the absolute value of x if I want to be right. But the point is they're inverse functions. The exponential function and the natural log function are inverse functions. So what this is here is really a composition of a function with its inverse, and that's why it equals y. How many remember, maybe, good question, Maria, how many remember maybe in pre-calculus when you take a composition of a function and its inverse, you get back the function, like? Okay, same kind of thing. So Maria, are you a little more comfortable with
I'm sure I will be. Thank you for that explanation.
Okay. All right. E to the fourth. Are there any other good questions?
Well, this part that we just got taught today, will this be in the exam on Tuesday?
This will be on the exam on Tuesday, Marcus. And what I'm going to do, actually, let me stop the recording here.